Hey guys, welcome back. Hey, we're starting week 2 of our extended e-learning environment here. We're going to wrap up during this week the topic of solids of revolution, and this time we're talking about solids that have a hole in the middle, and when we slice them, we get slices that we call washer slices. So we need to introduce that topic today. We're going to have two videos. This first one will be a little bit short, and we'll just walk through what a washer is, how we would find the volume of it, and maybe what the integration looks like. And then the second video will be some actual concrete examples, like problems we would solve using calculus. Okay, here we go. So maybe our first example of a solid of revolution with a hole inside it would be this kind of a situation here. Now this looks like maybe a roll of paper towel, or if it were a little bit shorter, something that's kind of scarce at the moment, a roll of toilet paper. But this example, we'll just make up some units here. The diameter of this cylinder is 20 and maybe 20 centimeters. And the distance from top to bottom is 50 and maybe 50 centimeters. Now the diameter of the hole is 10. Okay. Maybe I would encourage you to pause the video for just a minute here and consider how you would find the volume of just, if this were a paper towel roll, how would you find the volume of just the paper? Okay, now you've had a chance to think about that. Maybe a common way that most students would do this is to think of it as if it did not have a hole in it at first, and notice that the radius of the overall cylinder, the radius is 10, okay? And so I'm actually going to label that right here, and I'm going to label that with a capital R, because in a minute there's going to be a radius of the hole, which we'll be calling lowercase r. Anyway, this capital R is 10. And so you might start off by finding the volume of the whole cylinder. And so that would be to take pi times the large radius squared. That's pi times 10 squared times the height 50. Now that will give you the entire cylinder as if there was no hole in it, but we have to subtract the amount of the hollowed out section, which has a radius of 5. Okay, so let's label this radius little r. You probably can't read that, so we'll use red again. The little radius is 5. Okay, and so the volume of the hollowed out section, you think of it as a cylinder also, pi times its radius squared times the height again, 50. So a little phrase I like to use for this is we found the volume of the whole cylinder, the whole solid, and we subtracted the volume of the hole, spelled H-O-L-E, and we got the volume of what was left. Okay, now to write this as a formula here, the whole cylinder was pi times the large radius squared times the height of the cylinder, 50, and then the small, or the whole, H-O-L-E, was pi times the little radius squared times h. Now this is easy enough to follow along as it is, but for the purposes of what we're going to use this for today, I like to write this one more way, and that is to factor out the two parts that are common to both. Now you'll see why in a little bit, but for now I'm going to factor the pi kind of to the front end and the height to this end, and then that leaves in the middle the quantity big radius squared minus small radius squared. Now, it seems weird why I would pull one of those common factors to the left and one to the right. When we go to write the definite integral, you will see why I'm doing that. Okay, so anyway, this would be a formula we could actually use to find the volume of a bunch of these types of solids here. So now we're going to look at that type of shape again, but now we've noticed we've squished it down, made it much narrower, and we've rotated a little bit so that the center is now rotating around a horizontal axis. And that quantity we call the height of the roll of paper towel is now going to be called the width of this solid. And notice it's much thinner. What it more resembles in real life is what we would call a washer. You know, the thing you get at the hardware store made out of metal. It often goes with your nuts and bolts. Okay, so that's what this is. And so if you take our formula that we developed in the last page, notice that the washer has both a small radius, the radius of the inner circle, and a large radius, the radius of the outer circle in the cross section. And the little width, the little distance between the circles is now going to be, or the two edges is now going to be the width instead of the height. But I could take that expression from before and write this as pi times the big radius squared minus the small radius squared. And this time I'm going to express it as times the width and have it written this way. And the width is W. Okay, so what we want to do now is make a solid object made up and think of it as being sliced into hundreds or thousands of these types of cross sections. Let's see how that would look. And here we have a typical situation. Now what I've got is a graph showing a region in a plane. Think of this horizontal line as maybe the x-axis, but it could be another horizontal line. Today we'll only be working with it as if it was the x-axis, and maybe the y-axis is over here. Okay, so if you think of this as your coordinate plane, and so I probably have an equation graphing these two different curves. Maybe this is an equation of a line, and then there's some other equation graphing this bended curve under here. So we've got a region between them. And you notice we've got a little sliver of a rectangle again. We draw that quite often in problems involving integrals. But picture that little plane now, that little blue region revolving around this horizontal axis here. And I can visualize it over on the other picture by maybe redrawing that little rectangle in the place where it was. And now imagine that as you imagine rotating just that rectangle around the horizontal axis, which means the top of the rectangle makes a large circuit or trip around, and the bottom of the rectangle makes a little bit of a shorter trip. It goes around here. So you get this you see the little ring here, and then picture there would be a little bit of thickness to this ring, making it kind of like a washer. Okay, so the thickness of that ring is the same as the thickness as the width of that rectangle. And so in the process then, if we stacked rectangles straight across this region all the way across and rotated all of them, then I would be adding up the volume of all those washers to approximately have the volume of this solid. So essentially, the way we do the volume here will be the integrand will be from A to B, and the expression in the integral will be the same as the expression for the volume of our washer. Remember, the volume of our washer was pi. I'll even just remind you over here that the volume of a washer was pi times the quantity big R squared minus little r squared times the width W, or just write width. Okay. Now in our diagram, the width is the delta x, the change in x between the left side and right side of each of the slices. So we're going to end up with an integral that contains this same information. The integral is in the x-axis from A to B. The part that changes as we go across the region is how long is the big radius and the small radius. In this picture, the long radius or the big radius is always from the axis of rotation, such as the x-axis, all the way to the top of that rectangle, or in other words, to the upper function, the one furthest away from the axis. And the curve closest to the axis is going to help define the small radius. But those are the parts that change as I go from A to B. And so those are each going to be a function of x. So instead of just capital R squared minus little r squared, we're writing them in function notation, capital R of x squared minus little r of x squared. And then the expression for the width is really your delta x or dx in this integral. And then pi is something that will remain constant, and it can be written in front of the whole integral. And so this is going to be your template for a volume that can be sliced into washer cross sections revolved around a horizontal axis. Okay, so maybe we should make a note of that here. This is really for horizontal axis, such as the x-axis. If I were going to rotate around a vertical axis, such as the y-axis, it's really not a whole lot different, except that the radius of each of the circles will be a function of y, because I'll be slicing around this way. So this would really turn into capital R of y squared, and then little r of y squared, and then dy instead of dx. Okay? So what you'll notice is basically, if you look at this region again, if I were rotating around the y-axis or vertical axis, let's say now, so now we're going to rotate around here, the small radius would now be measured from this axis to the closest curve, which is this one. This would be now your little r of y. And the bigger distance across is going to be your capital R of y. Okay, we're going to go to the next video so we can look at a couple of concrete examples.